创造奇迹。
Hello, ladies and gentlemen. Sorry, I need to. Hello, ladies and gentlemen. This is Alice. I'm so glad to meet you on Friday evening in Beijing. And I can ask talks was already 1 more year, so we are happy to meet you every Friday. And we want to use the science and technology to connect world and the universe. This is Alice Zhang from Peking University, and I think I already here for a long, long time, and I'm almost every week here. And so proud to know all these top scientists from the whole world, and so proud to have them to give talks on this stage. And we have, August we have 5 speakers, and here, first week we have Chen Liangyi, then the next week was Terry. And then we have 2 young scientists from Africa and from MIT. And today is the last week and the last day of August. So we have Professor Liu Jing from Tsinghua University. And this was tonight our team. So I'm a moderator. We have 2 panelists, was from UCLA and from Shenzhen, was the South University of Science and Technology Guo Chuanfei, and we also have our challenger. So it will be a very nice, evening, because today the topic is very interesting. Professor Liu Jing from Tsinghua University, I know him more than 20 years, I think. Yeah, since that time I was still a student, I already heard Liu Jing's name because it is soundly. He got a bachelor degree in physics and also in engineering in Tsinghua University, and he got PhD there, and then he done a lot of nice work. But this liquid metal was one of his logo. I think it's a marker, because Liu Jing was, I think it's the first one, maybe in mainland China, even in the world, who done this work. And for about 20 years, he stayed in this field, make a lot of, nice achievement and get a lot of good results. Now also he's working for the industry, the commercialization for this technology. So I do want to use many times to introduce Liu Jing, because he will give his story. He has a very nice, slides to share with us. Liu Jing, please.
Good evening. Thank you very much, Professor Zhang. Yes, dear friends everywhere. So I'd like to thank Professor Zhang, Haixia Zhang, for his invitation. Actually, many times, really appreciate it. Thanks also to the panelists, Professor Guo, Professor Zheng, and Professor Wang, for organizing this talk. It is also my honor to join a group of distinguished speakers over the world to join the exciting ICANX to share our findings on science and thoughts about our research. So today, I'm going to discuss the topic of liquid metal science and technologies, from fundamentals to industrial practices. As you know, the liquid metal has gradually become very hot throughout the world. I guess quite a few pupils are considering entering this exciting field. So this talk, I'm going to present a relatively complete information, but for time schedules, I will not go in more details. Before my talk, I would like to thank my joint labs from the Technical Institute of Physics and Chemistry, the Chinese Academy of Science, as well as Tsinghua University, for more than 20 years strongest support for my research on liquid metal. So let's come to the talk itself. So what does the liquid metal look like? As we'll say, on the left-hand side, you will say the liquid metal in Hollywood science fiction film. This is a template, a well-known template, but it is not true, of course. On the left, also left-hand side, the lower part, this is a liquid at room temperature. You can say here, it is running inside the high-performance computer. This was made as a chip cooling devices in the year of 2005. And take a look at the right-hand side. So the liquid metal can look like a liquid, just like a droplet. It can also appear as a paste-like materials. In fact, we can have a couple of different liquid metal options in a wide range of temperatures, even like minus several dozens degrees below. So, and more, I guess, still can be found. The answers lies in the Professor Mendeleev's periodic table of elements. So as we will say, quite a few candidate elements can be used to make the liquid metal who will be in liquid at a room temperature. The most typical one is gallium. So here, this is 31 elements. Gallium, around here, you will see the indium, tin, lead, and some other mercury, quite a few things. So far, there's still a lot of secrets lying behind this table of elements. I guess we need to do more research to find out more secrets lying behind. Traditionally, people have tackled a lot of, quite a few classical room temperature liquid metals. Let's take a look at these tables. You will find is a mercury. As we say, it is in thermometer. It can also be found in the reactors as a coolant. And you will see some radiative element like the cesium and lutetium. This is radio. It's not safe actually, but it's useful quite a few times. And you can use the potassium and the sodium to make the alloy. The melting point would be like minus 11 centigrade. So in the year of 2009, we had ever introduced this material into the biological body for ablating the tumors. So you will see, although it is reactive, it is useful. And the mercury, its melting point is pretty low, like minus 38 centigrade. And we can make further lower point than this, actually. In this table, I would like to point out you to this parameter, self-extension. See here, the self-extension of gallium is 0.707. So this magnitude is pretty high, as you well know that. It is actually 10 times larger than the water. Quite a few many fascinating behaviors were just caused by these parameters. Of course, quite a few some other properties also very important. And of course, liquid metal metals can make as a noise. You will have many more options. Regarding the noise, we can now have a couple of candidate materials like the gallium-based alloy and also the bismuth-based alloy, including the tin-based alloys. Actually, there's quite a few options for making the alloys. In this case, you can have many options for your desires. So such materials are basically tackled, but now we have quite more understandings and much more materials were invented and made throughout the world. But one thing I should be make caution is that the liquid metals sometimes may cause corrosion to some materials. When we made the computer chip coolings, we find that liquid metal will corrode some metals like the aluminum or something like that. This is dangerous. So you must be careful when working or playing with some other liquid metal materials. So from this several examples, you will see that the sources for liquid metals are still very limited, very limited. They are still cannot fulfill every kind of needs we are facing. So that's why in the year of 2013, we proposed the idea of liquid metal material genomic. The purpose is trying to combine some theoretical prediction as well as experimental findings, aiming to get more materials for the industrial or some practical utilizations. This looks like some of the material genomic initiative. So far, we have got a series data banks for the liquid metals, some of the database have been released to the public. In the future, I guess such material option can be more and more found and be useful. So let's take a comparative evaluation of the liquid metals' basic properties with the most typical materials like the other metals like gold, silver, or some water, graphene, carbon-nanotube plastic, ceramics. So we will say if we combine all the properties together like electrical, magnetic, acoustic, optical, thermal, especially fluidic, chemical, mechanical, as well as nanos, we will find that liquid metals' answers to tackle such needs is yes, all is yes. But while for some other materials, only part of the answers will be yes. So in this way, in these cases, so liquid metal can be found very useful in a pretty wide range of very, very important areas. So regarding that, for example, in these slides, I will illustrate. So it's taking the fluidic, thermofluidic property as example, you will find liquid metal is very useful for the thermal management. That is for the chip cooling. If you take the chemical property as example, you'll find it is very useful. New kind of catalytic materials. And to take the electronics property as example, liquid metal is very useful for printed electronics, as well as some 3D printing for some functional, making some functional devices. Of course, liquid metal is very useful as a biomaterial because we have too many different options. Naturally, you will guess liquid metal should be an idealistic material for making soft robot, as just you have seen in the science fiction film, but it takes time. In the future, I guess more fields can still be extended in the coming time. So in this talk, I just give you some very typical examples as important science and applications. But before the applications, there are many fundamental issues need to be solved. So there are actually many secrets lying behind the liquid metal material and its composite behind, as well as the applications. So because we are lucky actually in this field for very long times. It is fortunate to, and also very exciting things to have some opportunity to get some findings as well as some applications, really a fantastic things. So let's take a look at the appearance of the liquid metals, some very fundamental property of liquid metal. The first thing is liquid metal is, of course, is liquid. It is flowable and looks just like water. So this picture gives a comparison between liquid metal and water. We had carried out a doping experiment. It is very unlike the water. This is because liquid metal, such as a gallium, it will be easily oxidized in the air. So when it is striking on the liquid metals, different flow features will be disclosed. And on the center of this video, you will see that liquid metal is easily drivable under the electricity, very low electricity, just the several voltage. And the liquid metal can have some striking impacting with some structures. This have quite a few physics problems. And one interesting thing is that when you drop the liquid metal droplet to the liquid metal pools, you will see that the droplet won't match with the same liquid metal pool. The answers comes from the solution because there is an interface between the droplet and the liquid metal pool. And the liquid metal pool is flowing actually, so it cannot match together. So this reminds us many things. Along this way, I have carried out quite a few fluidic studies. So this picture shows some flow patterns between the liquid metal droplet on the same liquid metal pools. And again, the liquid metal pools was covered with a thin layer of solutions, other solutions. So you will see that this is actually induced by the vertical vibration. Under the vibrations, a droplet just jump and come back again. So this will generate very profound flow patterns. And these patterns can be switched on or off by the electricity. This is very different from a classical fluidics. So their liquid metal raised quite a few, many different flow behaviors with existing fluidics. There are still too many issues to be tackled in these areas. So this slide, you can see that if we change the vibration magnitude and the frequency, you will see rather profound phenomenon can be induced, like this is actually we call as quantized orbital chasing behavior. You can see here, the two droplets will contact each other and flowing along the track. This track was induced by the oscillation. This is a pilot wave. And if the size of the droplet are different, larger or smaller, different behavior will be induced. This is looks like the macro scale quantum mechanics phenomenon. I guess this physicists, especially from the fluidic science, can have many discussed or thinking about this very interesting phenomena. So just to give you some basic impression about liquid metals. So just as I mentioned that liquid metal has very high surface tensions. So many external factors will induce very large, very evident variation of the surface tension. Those pictures show that the nanoparticles or some microscale particle, when placed on the surface of the liquid metal, it will induce flow. Because the nanoparticles will induce a polarization, so this equation shows that due to the aiding of the particles, it will induce a localized polarization of the surface. This will induce the surface tension variation and then lead to the pressure and drive the flow. So this picture also indicated that the particles can be applied as an image to trace the flow behaviors. Otherwise, we cannot know what happens inside and what happens to the fluid. To give you a surface tension behavior, I will give you a straightforward examples. Because liquid metal can have different reactions with the substrate. So on this videos, you can see that if we place the liquid metal on the glass, it will just stay as a droplet, spherical droplet. But if you put the liquid metal on the graphite, it will just lay down. In this way, we can make different structures using structure to make the triangle or lines, rectangle, or something like that. Otherwise, the liquid metal will rebound to its original shape. This is caused by the very high surface tensions. So in this case, we can use the electric field to guide the upload locomotions. Otherwise, it is not possible for some other materials. So this is just some of the very unique properties of liquid metals. And one very important behavior of a liquid metal is it is easily oxidized in the air. So if we partially immerse a liquid metal inside the solution while leaving part of its surface exposed to the outside, this will lead to oxidize the process and then resolve the process. So the oxidized layer of the liquid metal can be resolved by the solution, like the alkali solutions or something like that. This will induce the beating, just like a heart. We named this process as a breathing process. It actually harvests the energy to realize the beating, like a lung or some other beating forces. So this is just some of the physical chemical property of the liquid metals. And if we inject the liquid metal into the solutions, because of the high surface tension, it will be broken up into the droplet. This slide, or you can take a look at this videos on the left-hand side. So when you inject the liquid metal into the solutions, you will get droplet. Depends on your speed and the solution environment, you can realize a stream. You can realize a different structured droplet, like irregular, spherical. You can also make the wires or something like that. This way can be used as a manufacturing method. If you freeze them together, just like on the right-hand side, if you just freeze the droplet together, you will get the porous materials. So this is not only very fundamental, but also very useful for making some functional materials. And the injection process can be induced by electricity. This is the electrohydrodynamic shooting phenomenon. We found that under electricity, the liquid metals can be induced to jet or just the shooting like. Under this, what this happens though, happens under very low voltage, just like 2 or 3 or something like that. But with the increase of the electrical voltage, a very quick speed can be realized. This can also be used as to make some droplet. When you freeze, you will get the particles. This process is, of course, acted by the surface tension of the liquid metal. And if you think further, what will happen when the liquid metal droplet contact all together under 2 electrodes? We tried and we found that this will trigger some arc discharge plasma. That means some light will be induced. This actually can be used to make some display systems. So the earliest, in the first, we had attributed this as a plasma phenomenon. But with the time going on, we found that it belongs to a quantum photonic and acoustic effect, actually. So we can hear of the acoustic. So for this process, we have derived equations to characterize the process. I guess this quantum process can have quite a few thoughts or applications, and different light spectrum can be induced, I guess, in the futures, depends on the solutions and the liquid metal types, and also the charge, and also the electricity. So the former cases are basically the pure liquid metal as well as the solutions, but that cannot solve all the problems. So liquid metal composite materials is a basic answers. That means liquid metals can be combined with some other materials to make a couple of different functional materials. Basically, you can make like the plastic-like or metal-like or biological tissue-like materials, depends on you. So this is basic ways to make quite a few different things. Because of the liquid metals, fluidic, thermal, electrical can be used to tune other materials. But there are the 2 basic concepts to make such materials. One basic concept is nano liquid metal. This, in the year of 2007, we proposed this basic idea, nano liquid metal. That means liquid metal can be used as base fluid. Then we can just load quite a few other particles into the liquid metal to make some other functional materials, such as carbon nanotubes, metal particles into the liquid metal. We can make more conductive liquid metal composites. And of course, you can try more other particles. So this is used the liquid metal as a base fluid. But the liquid metal can also be used as filler. So in the year of 2014, we found that liquid metal can be continuously loaded into the silicon void. So we found that this can be used to make the thermally conductive with a highly electrically resistive grease. Then we proposed the liquid metal filler. Actually, liquid metal filler can be combined with some other polymers, more other material to make you want the material properties. But when you move to make the material, you will often encounter troubles. One thing is the challenge is to mix the particles with the liquid metal together. Previously, we are working on vigorously making the liquid metals with particles and introduced some basic approach to make, but we found that it's not efficient. Then we moved to some other ways. these pictures give you some three basic approaches to make the nanoliquid metals. So on the right-hand side, you will see that under the electricity, the liquid metal can eat in the outside copper particles, either in micro scale or nanoscale. So this is induced by the wetting behaviors between the liquid metal and the particles. So we will see that electricity can induce very large variation of the wetting behaviors. So it has quite a few applications. And meanwhile, we found that the chemical approach will also work. We can even add some chemical metals like the aluminum flake. This will also induce. The basic idea comes actually from the adhesion, wetting, or some surface tension issues actually. So this is basically the same. So in this way, we can make a couple of different functional materials. If we want the liquid metal to be conductive, you just load some of the, like a silver, copper, or some other metals, then you can make electronic inks actually. You can make the thermal interface materials. You can make some mechanically tolerable paste-like materials. And when you combine the liquid metal fillers with the silicons, you can see here a very large amount of liquid metal can be loaded into the silicon values, like even over 80%. So in this way, you can make the isolative materials, but with pretty high thermal conductivity. This is actually a very ideally the surface thermal information materials for the cooling, So it depends on the matching material. You can have different options. But when you test the temperature effects, some interesting phenomena happens. Because the liquid metal will expand after freeze. So if the material was combined with the silicons, when you freeze the composite, you will find that the previously isolated material will become conductive. This is because, take a look at the picture at the right-hand side there. So these two droplets won't conduct each other in liquid state, but when you freeze, they will expand and then finally contact each other. So this is a conductor. That means such a composite can change between conductor and isolated. So this is actually a liquid conductor insular transition material, as it is very important in a couple of electronic controlling environments, I guess. So this is just some of the basic information about the liquid metal it can offer. But unlike the traditional materials, so liquid metal can also be made as nanomaterials. But it is different with a classical rigid particle. It is a liquid. And most basic properties transformable. It is transformable, and it can easily switch between liquid and solid phase. So this is different, and it can adhere with some other materials, even like some biomedicines to make further useful material. So this is different with the classical nanomaterials. This also become new directions. If you introduce some chemical reaction mechanism into the composite, you will make a further very unique, very unconventional materials. So when we load the, let's say, the iron particle into the liquid metals, and we add some chemicals like the HCl, you will induce the chemical reaction. In this way, you can realize the porous liquid metal. This is just a liquid porous. This was made for the first time in the labs. So just like a lung, like the biological lung tissues. So it has porous inside, and this material can float in the liquid, in the waters. Through different ways, you can make quite a few different porous liquid metal. Of course, it can have quite a few different applications. It's just omit here. And if you combine some of the like hollow bubbles with a liquid, you will make further lightweight liquid metal. Because liquid metal is heavy, actually. It has 6 times larger density than the water. But if you combine the hollow bubbles with the liquid, you can make the density as only half of the water. Such kind of material can be floated on the water surface and to make some robotics or like some electronics underwater. So this is just the liquid metal can offer. Of course, liquid metal can also be made as a magnetic. You just load it through a proper way to realize magnetic liquid metal. And before freezing and heating, you will realize the solidified and the liquid magnetic flow. You can use this kind of material for the gripper, for manipulating the target. We name it as a liquid gripper. That means it can conformably adhere to very irregular structured target. So this is very efficient, very helpful for some manipulations. And most of the liquid metal are in white color, just like a metal, like a silver or something like that. If you want, that's why we want to make the liquid metal a little more beautiful. So we introduced the fluorine and the liquid metal combined. We can make a couple of different colorful liquid metals. And these colors can be combined to make a further more colors. This can be used as to make the biomedical channels. You can use the electricity to drive the flow of such materials inside the solutions. And you can use it as a colorful printed electronics, just to make it on the papers or some building walls, something like that. So this is just some of the examples I would like to share with you about the liquid metal. Such material has already opened many unconventional properties with the classical materials. So next, I will illustrate some very useful, very important applications actually liquid metal can offer to us, to the societies. The first area would be using the thermofluidic behavior of liquid metal for cooling the high-profile chips, devices, and systems. As everybody know that the chips is already too hot, actually, especially in this day and age. According to Moore's law, the integrity density already very, very high. The classical ways like the air cooling, heat pipe, water cooling won't work sometimes. This is a bottleneck. That's why people want to solve the thermal barriers facing the industries. So that's at the beginning of this century, I proposed the idea of using liquid metal for cooling the computers. This actually becomes the start of my research on liquid metals. Combined with the conventional cooling method, you can see here, heat pipe, water cooling. When the power density becomes too high, the heat pipe will be exploding and water will become boiling. But liquid metal won't just remain in liquid. This is because liquid metal can have, take a look at here, on the left-hand side, its melting point, its boiling point can be up to over 2000 centigrade. That means it will stay in liquid in a very, very wide temperature range. That's why liquid metal can sustain very extreme cooling. So this is a prototype we made at the early of the centuries. I think a very interesting point for the liquid metal to receive the recognition by the society is perhaps a chip cooling. So in the year of 2010, our design on computer chip cooling devices received an award from, this is the best people of the world from the ASM Journal of Electronic Packaging. At the time, I realized that quite a few people gradually realized the importance of liquid metal. Until now, it's already become very hard areas throughout the world. But in the old days, only very few labs are joining these areas. So this is just several commercially available products we made in the year around 2008. Quite a few have been sold out That was used for the desktop computers. But right now we are still, we have already translated the technology into the industry. They are trying to make some new products for the cooling of workstations or some mobile phone or something like that, even like notebook computers. So this is very useful. But I would say that liquid metal can also be used as a hybrid fluid. That means liquid metal can work together with some other waters or some other fluids. In this way, you can realize double cooling effects. But when you drive this flow, you will find some interesting, some unexpected phenomena will happen again. This is actually some of the folding patterns induced during the rotation of the liquid metal as well as the solutions. So you exactly. So for my experience, I always expect something will happen when we tackle some new issues. So this is just the science could tell us. So the frontier science will be happy when you tackle you expect to find something quite a few times. So liquid metal not just work as a liquid, it can also be made as just like a paste. So this is just some of the paste-like or some solidified thin sheet of paper looks like that. This can be used as a thermal interface materials. Also some conventionally available throughout the market. And we had under the invitation, write some book chapter you will like, you can check out. This is at the center, this is over 100 pages long chapters about the liquid metal cooling. Of course, you can also find some books on the liquid metal for more information. This is already more and more useful in quite a few areas. Next, very important areas, electronics. Liquid metal printed electronics is already very, very important right now. A great many outstanding labs have also entered into these areas. So, but it takes time to put the technology into wide, large-scale use. Actually, this we proposed this technology at almost the same time as a chip cooling, but it takes time for us to make out the tools and find out the ways to write the liquid metal on the substrate. And then when the breakthrough was made, the market immediately pay attention. But we need to educate the market. Then we can see here, slow down. And then we find that trouble, this elucement. This is natural gas for the installation verification. But we are now here. We have already come to the year of 2021. So this is actually the best time for the liquid metal printed electron, just using the liquid metal as an electronic ink to print out. Because tremendous labs have already joined, and a group of very, very interesting application has been published. So this is the best time. I guess tremendous things can be made true. The toughest things, challenges actually comes to the surface tension. So this picture shows that because liquid metal has surface tension pretty high, so it's usually hard to smoothly print it on the substrate. But this problem is already solved. Although it takes pretty long time, sometimes even takes like 8 years longer. But with the time going on, we have found a couple of different ways, like oxygenized or some components ways to tackle. And some fundamental issues also solved. Then so far we can print liquid metals on nearly all different substrates. At the early days, we have used the brush. We can print out just handwriting. Because you have solved the problem at haze and liquid metal on the substrate, you can print handwriting easily and freely. You can make resistor, capacitor, and the conductance. You can make a couple of functional circuits. In the future, so you can just write. So this is the ways liquid metal printed can offer. You can use handwriting, use a brush to print the thermocouples. This picture shows that if we print the gallium and the gallium alloy inks together, we can make some couples. This is based on the Seebeck effect. And the lead rate is pretty fine, and the resolution is very acceptable. And if you like, you can print out the artificial muscles. This actually was made by the electric elastomer actuator. This is because liquid metal is compliant, highly compliant liquid electrode. It is much better than the rigid electrode. It allows pretty large area strain change. This is very useful for making very high performance actuators. And this material can realize self-healing, if you like. This is just some of the tools we made. This is a rollable pen we made for quite a few people could use, freely use. And the materials, electronically, can be used as different, not just the gallium. We have also made the bismuth. That means if we write out the liquid metal circuit, after it was solidified, we can take it out from the substrate. So to show the easy going of the liquid metal writings, I will share a story with you. This is Mr. James. He's a former editor of Scientific American. When he found our technology, it's very interesting. Then he's trying to make the handwriting pen. And under my point by point suggestions, Mr. Chips do himself a writing pen and write himself some of the functional cycle. So this is very interesting. I mean, such kind of technology can be widely used even to the middle school. On the right-hand side, there is just some conventional available writing pen we made in the lab and then translated into the industry. Such kind of technology has actually received major changes to the society. This is Prime Minister Li Keqiang, this former president of the Chinese Academy of Science, Professor Bai Chunli. They're trying the liquid metal writing pen. This on the right-hand side is Vice Prime Minister Li Yanchao. He's looking at the products of the liquid metal. In the year of 2015, and of course, the pen cannot solve every problem. Then we begin to think about perhaps we need to make machines. That's why we proposed the 3D printing. Actually, this is the first ever proposition. See here, liquid metal printing. It is actually a hybrid printing. So this is a machine we developed. Actually, it can print simultaneously the liquid metal inks as well as packaging materials. Then you can compose different structured circuit like a bridge, set up a bridge to the three-dimensional surface to make different antennas, a couple of as you desire. But this machine is not automatic, fully automatic. Then we go to the fully automatic liquid metal print. This is actually based on another principle. We limit its taping mode. That means we press the liquid metal to the substrate and take off, then press. We have also, this depends on the delivery of the liquid metal until to the target substrate. And of course, the pressure, some of the expanded conditions will affect the resolution. At that time, the printed resolution looks like 200 micrometers. But now, for the commercially reliable available machine, is already 20 micrometers, pretty high surface tension, high resolution. This is just some of the circuit we made, like Merry Christmas card, some display, some functional electronics, Great Wall, White House, whatever if you want, just use just like a print in the office or in a home. So this kind of technology can be available everywhere. So in the year of 2014, we have exhibited this machine in the China, the most important international industry fair. So this is the machines. This is an exhibition. This is a vice president of the Chinese Academy of Science. This is my student. This is our machine. From the time such kind of machine has received graduate attentions of the society, and now it has been gradually widely used throughout China, except for the 2D printing or the circuit printing. We had also proposed some 3D printing methods and machines. On the left-hand side, this is a liquid phase 3D printing. That means we can print liquid metals inside the solution. Because of the cooling effect of the solution, we can quickly make the metal structures in 3 dimensions. And we can also make the hybrid. That means because liquid metal has no melting point, we can simultaneously print them with packaging material. In this case, we can make very complicated functional device. And you can also make the liquid metal in the gels. So you can take a look at this video on the right-hand side. The liquid metal was just printed inside the gels. It can realize different structures, soft. Okay, so we received encouragement from society actually. The invention of the liquid metal print has received like the RD 100 awards finalist, and also from some other domestic awards. So it received wide attention. We are very happy such machines can be helpful to society. This video just for some working of such machines. Right now, very high performance has already been available. But one basic question we should ask, can we make the liquid metal circuits different with the existing rigid one? The answer is of course. So actually liquid metal electron can be printed on nearly all different solid surfaces. So this is the atomic spring liquid metal printing we proposed. This is MIT technology view. The story says this kind of technology can be used to print circuit on nearly different substrate. This cannot be done by the traditional methods. So we have already made the circuit on a couple of like glass 3-dimensional substrate, and also some other even leaf closes or some other like things. You can use this to package some commercial products. Depends on your process, you can make the transparent electrode. So you can make, depends on the deposition process. And under the pressure, as with a screen, you can make a couple complicated within just a very quick time, just a few seconds. You can make, use it to make the chemical or biochemical sensors, as well as some, combining with some other biosymbols, you can make the glucose detection applications. Of course, if you like, you can print the liquid metal circuits on the wall of the building, your home, your ground, and the clothes to make the wearable Internet of the things. So this is a basic tools. But sometimes we will want to print the metals to the irregular surface. We have to introduce transfer printing. A couple of transfer printing has so far been developed to, based on some physical effects like the freeze to enhance the adhesion. And we also developed some selective transfer printing based on some matching material like PMA, depends on the adhesive behavior between the liquid metal and the material as well as the substrate. It can transfer printing the liquid metal to the target surface like a paper electronics. And such process can be quickly printed, depends on a couple of delivery methods. Some of the methods has already been labeled as a smart printing. For very complicated circuit, just can be finished within just 10 seconds sometimes. So in the long run, liquid metal can be used as an integrated circuit printing. this is just some of the trials in my lab. In the future, so we hope to offer such kind of basic tools, including some very high resolution circuit transistor, like 2D materials. We also try, along with the industries, such kind of technology. I'm very happy to see that quite a few schools throughout China have gradually accepted this kind of technology. In this slide, you can see here, the image, very complicated circuit. It was just printed out in just 10 seconds. I think another very important area is biomaterials. Namely, it is new weapons to tackle biomedical challenges. So the example are rather diverse. Previously, people even don't think it is an area, but now it is already become very important. They are from head to the brain to the legs. You can make the sensors, electrical skin, nerve connections, tumor treatment, quite a few things. So this is brand new materials like wearable sensors for healthcare and stretchable electronics for a couple of different purposes. You can even print the liquid metal circuits on the fibers to use it as a motion monitoring. This picture shows a direct deposition of liquid metal circuits on the skin. This was developed to treat the melanoma, very challenging tumors. Under the very low voltage, it is possible to destroy the tumors. In the future, so we can print such a circuit on the skin to realize different medical purposes. And some, just for healthcare or interactive electronics. So this was made available right now for printing the liquid metal circuits on the skin. This was realized by the selective printing method. For the implanted, I think I should speed up and speak. So implanted, we had proposed liquid metal as a connecting medium. So under the help of the liquid metal, electrical signal can be transported, delivered to the other part. So this research is actually make us better think about the role of liquid metal in the very challenging biomedical issues. So this is a soft electrode we made. This kind of tank has already been used to stimulate the frog. Actually, this is a already died frog, but under the stimulation of the electrode, it looks just like alive, actually. This is a soft. This can be very beneficial for the biological applications in the futures. This picture shows some imaging contrast. Because the liquid has high density, we can have very high resolution imaging contrast. And such kind of liquid metal can be used to block the flow of the blood. This way, you can starve tumors to death. A couple of animals test has already demonstrated the feasibility of such method. If you want to use the mechanical behavior of the liquid, you can just realize injectable bone. That means you inject the liquid. After it was solidified, you make the bones inside. And this is the injectable electronics. You can make very complicated electronics just via the minimally invasive printing of a liquid metal on the human body. And for the outside, you can make the wearable exoskeleton. That means we can easily hit to conform to the human body and then fix it. Okay, I think I need to be quick. The last area, I guess, very cool, also very important, is liquid metal machine, soft machine. All the stories happens because of the discovery of transformation of liquid metals. We had named liquid machines, and the society thinks this is promising new era of soft robots. This has become already more and more promising, actually. So this is just some of the videos. Is early of the 2014, we published a paper with many videos. You can check out the video, actually. From these videos, you can find liquid metal can transform among different configurations, from large to small, from symbiont to droplet, and the rotational motions, and running across a structure, the bridge-like structure, or match together. And this process can be reversible under the help of the chemical environment, from large to small, and then go back. If you like, you can use the liquid metal as a wheels to drive the 3D printed small vehicles. You can drive the vehicles using the liquid metal wheels. This looks like a interesting advances. So the chemistry say it is a big advances. Of course, we are happy. I think the most fascinating phenomenon for liquid metal is perhaps the self-fueled liquid metal. It is under the continuous we could find that when eating some aluminum inside, liquid metal will have generate energy. This is actually a primary battery effect. Then it will self-running here and there and lasting pretty long time. So this really very amazing. Sometimes we think about this phenomenon. This is because the liquid metal has a high surface tension and also chemical reaction rate. This can be, of course, made different vehicles, merging together, separated together. Quite a few interesting phenomena was found. If we like insert wires into the liquid metal, you will find that the wires will just keep oscillation, just like a violin, like oscillate. And this oscillation frequency and method can be regulated by another metal. This is just some very unique behaviors happen on the liquid metal machines. And such a machine can be even made tiny motors. If you inject a large metal, liquid metal machine into tiny motors, droplet, you will see here, just like a spirit. This is a swarm of liquid machines running inside the channels. If we use some optical contrasting experiment, we find some behaviors where they're very interesting. This looks like a Brownian motion, actually. We have used some image contrast to characterize such behaviors. And this behavior can be controlled by the electricity, just like a bullet. Under the electricity, because liquid metal is a large body of electrons, so under electricity, you can easily driven to flow towards certain directions. So if we make a comparison between the classical Millikan's experiment with current liquid metal motors experiment, we can estimate actually the electrons on the liquid metal surface. There's still a lot of fluidics lying behind. If we test its magnetic field, we can find the magnet will serve as a trip. This is because liquid metal is an electron body. So under the Lorentz force, it will be rebounced back. This is just to open some new physics in the future. But the people would ask, can liquid metal be used as making software? This is true. So you can make a large-sized software machines. This is just several examples my students made. There are some sensing capability as well, running actuations, and even jumping based on the liquid metal energies. And it depends on some materials program. We can make the program of liquid metal materials. You can just make different structures to make whatever, some structures, soft machines or soft robots. Regarding the liquid metal robot, we have proposed actually a very fundamental idea because liquid metal is a very special intelligent liquid. We had proposed that liquid metal should be combined with some of the materials to make even further advanced robot. This just looks just like iLife. That means intelligent liquid metal integrated functional intelligent. This is in comparison with a solid integrated circuits. So yeah, I guess in the last part, just in several minutes, I will give you some information about consideration towards about the industrial practice. In about 10 or 12 or 14 years before we are in Beijing, I had ever thought about to establish the liquid metal valley, but this dream became true in Yunnan province until about 8 years before. So this is a location of a liquid metal valley. Here we can find the world's highest bridge in the liquid metal valley. Actually, this is my hometown. I hope in the future I can have a chance to welcome you to visit my hometown. This is Yunnan province is very special for developing the liquid metal industry. First, it is regarded as one of the most beautiful provinces in China. It is also kingdom of animals and also kingdom of plants. The most important of all is Yunnan province. In China, it is a kingdom of non-ferrous metals. That means we can find a great many different metal sources to make liquid metals. That's also one of the most important reasons we develop a liquid metal valley in Yunnan province. And so far, quite a few high educational agencies, top universities like Tsinghua University, University of Chinese Academy of Sciences, and quite a few other universities are joined to set up the liquid metal valleys. And a couple of research centers, labs, companies, and science museums have been set up in liquid metal valley. This is just some of the exhibition centers. Quite a few technologies have been developed here. And some leading product lines for fabricating liquid metal materials and devices have been set up. And we have also held a several milestone academic conference, Industrial Summit Forum, and the exhibition in liquid metal. This is just some of the equipment we exhibited. And some product has also been used throughout the world, such as a Sony company or some of the top companies has used some of the products, such as thermal interface materials. And for some healthcare products, it's also possible. Previously, it takes time, but now healthcare also quite a few products has been used in clinics. So summary, I guess if we historically, if we have the Bronze Age, Iron Age, in about 10 years, I had expected perhaps we can have a liquid metal age, but this depends on more and more efforts in the futures. So that's what I wish to share with you. Thank you very much for your attention.
Thank you very much, Professor Liu. That's really a lot of information and many interesting work. Today we got a high attention on the internet. Many people would listen to your talk. And then now a lot of questions come out. I pick up some of them. So the first question I say is from Nancy. As they are major players in microfluidics. So she is asking for, what's the fundamental of the liquid metal droplet generator? Yeah, you generated a liquid metal droplet. Can you tell some fundamental story how to make it?
Solution will make this happen. Because a liquid metal has 10 times larger surface tension with, for example, the solution, the water, alkali or something like that. So it will break up into droplet. But if you inject with very high velocity, you will realize that wire-like structures. Depends on your process.
Okay. Yeah. I think
this Nancy should be working in the industry. Yeah, so she's worry more about how to control the process, how to control like the dimensions of these things, in precision. Thank you very much for your answer. And the next question is from Wu Lidong, I think is his name. I don't know where he's from. Is what kind of liquid metal, nano composites are promising in the future? Yeah, I think the next question you already answered some. So please answer the first. What kind of liquid metal nano composites are promising?
Yeah, that's a good question. Liquid metal can, as I said, can be made as tiny as possible because it's liquid. So this is unlike the traditional rigid particles. So you can find some easygoing ways to make the micro nano particle, like ultrasound or some lasers or some beams. You can make even smaller droplet actually. But when you freeze, you will get particles. But sometimes you have to be careful about the solution environment. You can try to introduce some silicon. Without the silicon, the particles will match together.
Okay, yeah. Maybe I ask a question the following this one. I mean, you just say that in Yunnan, your hometown, there are kingdom of the metals, right? Different metals. So is all kind of metals can be made for this, liquid metal, or is it just some kind of elements can made it?
Yeah, this is a big question. So far, just a part of the metals can be combined to make the liquid metals. But for the smaller ones, we had proposed the idea of softening. Hopefully, we can find more options to make the liquid metal or room temperature liquid metals. But so far, just as I just explained, like the gallium-based alloy or bismuth-based alloy. But for the minus centigrade, so that like the mercury can also be made as a composite alloy. So we had written a book to explain the liquid metal at a very low temperature, like minus 17 centigrade. But it is toxic sometimes. So we have to balance between the useful and also the safety.
Okay, very great. Yeah, the next question, the third question is, there are many reviews on liquid metal, and some of them mention that liquid metal can be used as a catalyst. But so few work, not a lot of work focused on this. Can you comment on this? And if liquid metal really suitable for catalytic applications, especially electro catalysts?
Yeah, this is very possible. Yeah, because many metals can be used as a catalyst. And for our works, we found that liquid metal, when filled with aluminum, it will enhance the aluminum to generate hydrogen, but without consumption. In this case, liquid metal can serve as a catalyst for the aluminum water reaction. This is a catalyst. And for liquid metal, it is flowable and liquid. It can be found in quite a few different areas. As it's transformable, it will provide more options. Quite a few outstanding labs have entered this study, and excellent work has been published. I guess in the future, more options for the liquid metal can still be found. So catalyst is a good way, yeah. It is not like the rigid metal. I would encourage, more work. Yeah, we had write a review paper on the liquid metal catalyst. If the readers colleagues like to check, you can. But in the future, I guess, as just Professor Zhang said, still needs more efforts to pick out more.
Okay, great. So, Jing, that's a question was like for one. Now we have our panelists will be get on the stage. So first, as I introduced Xiaoyu Zheng, Jenny was from UCLA. He is, super expert in the 3D printing, print a lot of metal materials, ultra, light and ultra strong, metal materials. He's expert here. Use 3D, printing a lot. So I think it will, get more questions for how to print liquid metal with you. And next, our panelist is Chuanfei Guo. Professor Guo was from Southern University of Science and Technology, and is a super, young professor and a superstar in the soft robots. He uses, metal materials and all these kind of liquid metals a lot. And we have our challengers, Binghao Wang. Dr. Binghao Wang was from Southeast University. Now is a young faculty there. So welcome all of you join us, get on the stage. Yeah, please turn on your microphone and turn on your camera. Binghao, are you ready?
Yeah, sure.
Binghao, yeah, as usual, we welcome you to, ask the first questions, our challenger, please.
Okay. Thank you for making the science so fun. Actually, I learned a lot during your talk, and actually, I saved a lot of pictures for future learning. And actually, the liquid metal features both high mobility and high conductivity. And I believe the liquid metal industry will become true in the near future. If I learn correct, the liquid metal have different metal points, right?
Right.
Yeah, they are either fluidic or either solid in the at the room temperature.
Yes.
Yes. So my first challenging question is about solid liquid metal. For the industrial application, as you know, the cost is very important. However, when compared to cheap metals or plastic, the manufacturing or the value of the liquid metal we use is actually costly. So it will make it hard for businessmen to use such materials. And on the other hand, the functionality of the liquid metal is not replaceable. So
recyclable, you mean?
Yeah, it's not. It's I mean, it's some other materials can replace liquid metals. For example, I know the ideas about the printing liquid metal or your use as a cooler is very exciting. So, but how can the solid liquid metal to find its way to truly success? I mean to making a wider acceptable commercial products.
Yeah, very good questions. Your first question is the cost issues.
Yeah.
Yeah, this is really very important. Does matter for the industry. But actually, before the tremendous work, actually the liquid metal was not fully used, actually. In fact, such kind of liquid metal, the basic elements are profound in the earth. That means we have sufficient material sources for the applications in futures. In the past days, because the liquid metal was significantly neglected, people even do not want to use it. Actually, we have too many. We have a couple of options. But for the application like the printed electronics, actually it is very low cost. Without wasting, you just print them out. Only very limited are used. This is pretty cost effective. Your second question is, I forgot. I forgot. Yeah, I should write it down.
Yeah. No problem. We need to have the question keep short. Okay. Yeah. I think here I got another question is very important from the audience. Sorry for this travel challenges. It's Lu Jian. He's asking how to avoid the effect of a low temperature, on the liquid metal. Yeah.
The melting point.
Yeah, he's trying to how to avoid the effect of the low temperature, during the printing.
Yeah, the application. This depends on the situation you are working on. Sometimes you have to, actually, liquid metal provide new options for applications. So you have to find new applications, and those applications cannot be replaced by the existing. For example, just as I mentioned, chip cooling. The solid conduction cannot tackle the very tough challenges like a thermal barrier. You have to use a solution to deliver the transfer the heat away. So liquid metal can be used. It can be remain in liquid until up to 2,000 centigrade. Sometimes you can have very big powers. So you have to use a liquid metal. But for example, the transplanted biomedical technology, you can use the liquid as an electrode. If you use a solid electrode, you will feel very comfortable. For some biomedical applications that solved even liquid, you will have, for example, the Young's modulus as close as to the tissues. So this is very beneficial for the applications. And for some stretchable electronics, you can just use a liquid. Let me give you examples. If you make some actuator, if you use a liquid as electrode, the liquid electrode will be compliant with the actuation. For the rigid ones, it will stop, will resist. And of course, there are quite a few different situations. What we need to do is just to find out the best way. But I should say that liquid metal cannot solve everything. We need to do is just to find out the best way to use it.
Yeah, that's really, really good. So yeah, now Rennie, so Rennie, can you hear me? Yeah. So
yeah, I can hear
early
you.
morning. Yeah. So please. Yeah.
Great. Yeah, very nice talk. I learned a lot from your talk. So I do have one question, two questions. So first, also related to the microelectronics. So we've seen a lot of liquid metal being used to make, stretchable electronics, soft robotics. So they're really cool demos, right? So, but how do you, I guess it's still very hard to replace microelectronics industry where people just basically use PCB board or other screen printing type of technique to make more scalable electronics products. So can you comment on the scalability of liquid metal printing and what are the challenges you need to overcome to actually mass produce or make the printing industry more scalable so that people can be more drawn to liquid metal printing?
Yeah, this is a very important question. Actually, liquid metal can be made as small as possible, even like the nano electrons, but its repeatability and reliability is not good enough. Especially for the industrial practice, you have to guarantee the reliability of the circuit you printed out. That's why the industry, our collaborators has taken too much time to just want to make sure the machine can print out the same things on the different situation. Reliability is another thing. But for the lab test, actually you can make as tiny as possible. This depends on the printing pen, the printing machine, printing method. Sometimes you can use transfer printing, so you can make. But I also gave illustrated one example to print the 2D, two-dimensional liquid metal on the substrate. Because the liquid metal can be easily oxidized, that thin layer is semiconducting and with very good energy band. So actually we have already been able to print just very tiny transistors, but this is just the lab, just for lab trial, not for industry. For industry, we have to guarantee. But for those machines we have, that is already past the industrial demonstrations. So some machines already been reliable, but in the futures, tremendous efforts are still to lead it. I guess that should be a combined contribution from material itself, machine itself, and so also some principle actually.
Thanks. And for scalable,
please.
For scalable productions, let's say if you want to print hundreds, thousands of these parts, right, using liquid metal printing method, will there be approach such like maybe use injection molding to inject liquid metal or other method that you can envisionalize in the future that you can mass produce this type of thing? I guess that's the primary challenge is you can't really print a lot of liquid metal electronics just like you do in the microelectronics fabrication industry, right?
Yes. Regarding the liquid metal printing, it is unique license that pervasively available. So if we can help everyone can use such kind of machines, that will significantly stimulate the work of the students, even middle school students. So at this time, at this stage, yeah, it is still a little distance from the microelectronics. But in the future, with the research going on, such possibility possible, I guess.
Okay. I didn't tell you, yeah. For this, printing process, exactly like a 3D printing, it's the same problem, right? Yeah, if you want to print a lot, in the mass productions, that's a really tough job, right? But you always have some special, part you can use it. Liquid metal is the same thing. Yeah, liquid metal has its own advantage and also can be used to print it, some volume, maybe not that large, volume we expect.
Yeah.
Yeah, but also I would like to add is it can simultaneously print it with other materials because of its no melting point. That means we can print together the liquid metal inks, of course, with different melting point, with other plastics or polymers or rubbers. So this is unique with other existing ways. In that case, you will print out the targeted functional device. In the future, I hope all this process can be automatically printed out without interruption by the humans in the future. I hope
that time will be mass production.
Right, you can help. Yeah, Professor Chen, you can help.
Yeah, I was just thinking maybe I don't know much about this liquid metal field, but is there other alternative approaches to printing where you can just inject liquid metal to other shapes using molding techniques? Maybe that will be easier.
Yeah, you can print. That is also one basic way. I did not show you. You can make the tiny channels, just a microfluidic channel. You can just
inject, right.
Yeah. You can even use some nano structure to transfer printing. You can make a very small structure. Yeah, we can borrow some ideas from the existing.
For sure. Okay, well, Professor Guo, Chuanfei, yeah.
All right. Okay. Very nice talk, Professor Liu. We know that liquid alloys will have a lot of applications, such as in electronics, in software robotics, and in biomedical engineering. Okay. So, in your mind, what is the most promising application for liquid alloy?
Thank you. This question was also very interesting, actually. So in my side, at this time, I think the liquid metal electronics may be the most interesting things to be useful, because we can find like the liquid metal printer has been extensively used throughout the China, let's say, several dozen universities. So students are very happy, and we are very happy because this machine can be, because it can be used to print electronics at anywhere and anytime,
Yes.
and also any surface sometimes with a very low cost. So this is very important. But yeah, so we hope it can be. But for the applications, I should mention that liquid metal is very useful, not just for research, such as liquid metal cooling. That is very useful, especially for some chips, machines. Actually, some of the product has been gradually translated. So people say that it may be the time for the liquid metal cooling. Actually, it takes almost 20 years right now. But in the future, I guess liquid metal biomedical technology will be cool, such as brain-computer interfaces. So, but it needs time. In the future, so perhaps soft robots, highly advanced robots, will be also very interesting. Yeah, I guess this depends on a lot of research and practices. So far, quite a few practical technology has been, hopefully they can help some people.
So this one was follow you long time, and she also reported his question in several platforms. So I have to ask her questions. As Hu Dan Tang was from Henan Polytech University. She is asking for if there is any research for the damage calculation of liquid metal. For the lifetime of this kind of calculation. Yeah.
Perhaps he asked the question for the biocompatibility, I guess.
No, he's asking for the the lifetime of the damage. Yeah, the damage calculation.
Right?
Yeah. I guess this is different sides. So for some of the liquid metal, like the Genome, it will be oxidized, but it won't be damaged actually. So it will not evaporate. So it will just stay there. So such kind of liquid metal material will be disappear. When it disappear, it can be recyclable. So it's not, but it may be cause some corrosion. You will be careful with some aluminum. That's the one thing. But when you use it with biomedicals, you will be you have to care about its biocompatibility. But we have different options. Some material has already been tested in the animals for even like 8 months longer time, and it is safe. And research are still going on to find some other new materials. It is possible because wide range of material can be selected. Let's work together. More people.
Okay, well done. And many, a lot of, audience was reported here. They read your book, they follow your work, and a lot of, fans here. So I have one question for you. It's Liu Jing. I know you many years. I know you many of your students, are getting, superstars. Yeah. So can you tell us something how to, educate the students and to be superstars? Not only yourself, to be a superstar, but also you have a, nursing a group,
Thank you for your questions. I guess first, because this student are talented student, I'm very happy to meet such a group of talented students throughout China. So this is the first one. Second, I guess they are very active, especially for the research, fundamental science. I think one one answer is perhaps the frontier science will offer opportunities. And because the students are trying to learn new things, trying to find new things. And in my lab, actually, I'm trying to set up the atmosphere with multidisciplinary. Because my background is physics, engineering, and biomedical, I'm trying to, we are a lab with different areas. So with sparkles, discussions, this. Yeah, one thing I'd like to share is because it's a frontier science, it has a lot of unknowns. I often said, I'm sure something will happen, although I don't know when it will happen, but we just go ahead. Then from biological, this is, so sometimes we just said we are lucky. And even we have to appreciate why nature has offered such a fantastic material for us to work on and have some findings. So because liquid metal, I guess, liquid metals can help.
Okay, Liu Jing, I use one Chinese word, you 凡尔赛. Okay. You're really fine. You got, you say you're lucky, but a lot of people want to be lucky, right? Yeah, so I say that I know you 20 years ago. That time you already start to work on this liquid metal, this fashion topic. But fashion topic always meanings is disappears very fast too. But you make it, for 20 years, you stick on one topic, right? But major one topic for such a long time. So yeah, can you tell us what make you stick with this topic, liquid metal, 20 years? What's the magic?
Yeah. Actually, I started to investigate liquid metal. That is because my lab. When I set up my lab, originally we are trying to work out the biomedical equipment. We want to help some people, but then I find it takes pretty long time. Then I have to find new directions to help my lab to survive. Because of my major background is physics, thermal science, and bioengineering. So I conceived. I actually, in the early days, I had ever written a book on micro nanoscale heat transfer. The purpose is just want to cool the computers, but I'm not satisfied with the existing methods. So finally, of course, it takes some time. I went to the liquid metal. That is, liquid metal cooling is the start of our works in this area. But when you're doing experiment, sometimes you will make your hands dirty on. The liquid metals will frequently actually dropped off to the spring computers and the smell of the computer. Then you occur the idea to use it as electronics. This is one by one.
Okay, I see.
I have one more
a lot of stories. But in Tsinghua University, some of my students are biomedical engineers. I want to try liquid metal, whether liquid metal can be used as biomaterial. Then we doing some trials. So that's why, but finally, we survived.
Good. Okay, translate, please.
Yeah. You just talked about you have worked in liquid metals for like 20 years, and of course you will you must have faced a lot of stories during your research, and you just told us that you have some stories, right? So my question is, what is the most interesting story during your life in the last 10 years?
Thank you very much.
Or you can also tell a story in the last 20 years. That's also fine.
Actually, this story, the science story is very interesting. And also very, perhaps can be of a certain reference for others. I think the most exciting things in the research is unexpected discovery. Unexpected discovery. So this is really very exciting. So I would like to share one thing is our work on the liquid metal biomedical materials. We are first tries to, just want to use a liquid metal to serve as a nerve, to connect the damaged nerves. Just want to deliver the electrical signals. So because the nerves is biological fraud, it is in solutions. When we use the electricity to stimulate the liquid metal, we find it's transformed. So that's actually next to the discovery of the transformation of liquid metal. But our original try is not to make the transformer. Then a group of subsequent discoveries found, even like programmable material, cell-fueled liquid metal, tiny motors. So this is just, I mentioned, the fundamental science, new science will give you unexpected discovery. This is the most interesting thing. But some of the also very interesting, but not a pleasant experience. For example, just I mentioned, when we're doing experiment, but until now, my students still, gets the hands dirty on because of the liquid metal. But when I should be appreciated this experience in my early trial to make the liquid metal cooling device, because the liquid metal was dropped to the computer screen. It cannot be wiped off. This reminds me, we can use it to be as electronic inks. So as this actually led to our trials of the liquid metal manufacturers. Some other interesting things would be like the publication process. Actually, just as I mentioned, we had the user using the liquid metal as connecting the damaged nerves. This is a brief trials. Actually, this work received tremendous attention throughout the world. It was reported by nearly all the top science news, but it takes pretty long time to complete this work. I had assigned my student in Chinese Academy of Science, as well as Tsinghua University Science. It takes almost 3 years to complete the work. But when we submitted the paper, it was accepted, actually, several times. But just as I said,
everyone has a story.
I have to,
Yeah.
so finally,
So next week. Yeah. Okay. Jing. Yeah. So next Monday will be your students. Wang Hongzhang will talk about this story on the Monday's talk for the IKX breakers. Yeah, I'll talk how to publish the papers, based on, tens of the works and many turn down rejections. He will talk about that, in next Monday.
Yes, sometimes the original work, one to accept it is reasonable.
Yeah.
But because it is an original work, you will receive recognition, attention. That is rewarding. I guess that is rewarding.
Yeah, a lot of times actually the people who is reject your papers, that time they give you a lot of comments.
Right.
They try to push your work into a new level. I think that's sometimes it really happens.
Yeah.
Okay, I see. Yeah. So now, So any more questions? We are already past about 10 minutes. Okay. Yeah.
Yeah, I do have a question. Thank you for
Okay,
sharing
please.
this interesting story. But here I have another challenging questions. In the past few years, we have seen the bloom of the wearable flexible electronics, and actually because the unique features of the liquid metal, it becomes the most studied materials. So, however, for the wearable product, except some smartwatches or ring band, it's not very acceptable for most people. So that means most people do not want to wear it or buy it. So what's your thought about the future of the wearable electronics and the future of your liquid metals in this field? Thank you.
This was a big issue. I guess that depends on real needs. So people need help, but this needs help existing ways cannot offer. That's a must. That we will have to think about the must. So for the wearable electronics, just actually about 10 years we had ever tried to mobile phone, biomedical technology. We developed a couple of, but when you time's going on, you will feel tired of such applications. But for those like the tumors or like the brain-computer interface, nerves, I encounter a couple of different people's tumors. How to destroy the tumors, treat the tumors. And neurons, especially when neurons was damaged, this body cannot respond.
Yeah.
It's a very sad thing. If you can help them, that is a must live. So in the future, one thing, but liquid metal or wearable electrode does help for some like activity, motions or some walkings or runnings or something. That is also interesting things. People have different needs. For commercial product, you have to find out the way people really need. And some is for long-term need, some are just for short-term needs. So because we have a couple of interaction with the society industry, there is a tremendous tons of questions for us to answer sometimes, but we just find out the right needs, then maybe the product can be successful in the future.
Yeah, I think I love Liu Jing's answers that reply. Actually, for all these kind of advanced technologies, emerging technologies, they really need to find the killer applications. What's
the killer applications.
Yeah, what's a must? Then that can replace. So sometimes you must find that part. I think like liquid metal. Why we so love liquid metal? Because liquid metal has a super advantage. It's being flexible, solid, and reconfiguration, right? Yeah, it can do all these kind of things in transformer. I think that's very important for like the things in software robots and in the eye life, right? Intelligent, life. All this kind of research. You must need this kind of, materials, technologies. I think we can find some kind of unique application here. If we found that we do, use advantage of this liquid metal or even softer material, even, like a wearable, electronics or something, if you solve that, problem, the must, the killer applications is right there. I think, we need to find some, kind of application areas or products or functions, like this.
Right. I would like to share two examples with you because it's really important. One example is thermal interface materials. According to Huawei, the number one companies, they said they have no other possible solutions but just the liquid metal thermal interface because it's the highest conductive, but takes almost 20 years to make it industrially used. Another example, successful perhaps, is for the immediate printing out. Because the universities throughout China, previously, the student cannot make the circuit in class because it's a very complicated procedure. But right now, with such machines, the teachers, after the teachers told the students, they can make themselves quickly. This is some of the examples. Perhaps can partially.
Okay, very good. So thank you all of you. And time fly. We really have a very good, panel discussion, and we have many questions. We still have some questions online. So Liu Jing, I will send to you later, so you can ask that questions.
Okay.
Thank you, everyone. And we do enjoy the panel discussion. We do enjoy the liquid metal and all this new technique. And Liu Jing, as usual, I will deliver this, the certification to you. This was ICANX tradition. Every time we will deliver a certification to our super speakers. So, Jing, you deserve that because you use your liquid metal science and technology for fundamental to industry practice. That's an honor for you. To be our ICANX speaker.
I appreciate it very much.
Thank you very much. Thank you. So next week we will have another superstar. We will have Professor John Rogers. I think in soft flexible electronics, everyone knows his name as one of the super scientists in the whole world. And he's going to talk us stories about the functional nanomaterials and the 3D narrow interface. So this should be a great talk. And next week we will have a Paul with my partner to be moderator. We will have Jing Yu from City University of Hong Kong. And we will have Sheng Xin was from Tsinghua as panelist. We will have our challenger is Ling Wei from Tianjin University. So welcome next week, and I see you again. So this was all of tonight. And thank you all the audience. I know all of you from the whole world joined this, and many questions and many discussions. Welcome to stay with us every Friday. Thank you. See you next Friday.